Swayam Prabha. Digital India. Educated India.
Welcome to module 7. In module 6, we looked into the strength properties or strength related properties of concrete, and in this module, module 7, we shall be looking into creep and shrinkage of concrete, two other important properties, or rather behavior of concrete. And in the first lecture, we will start with creep, and outline of this lecture is first we will talk about or rather we will introduce creep. There is something called relaxation, we will also talk about that, mechanism of creep as much as possible, effect of various factors, aggregate modulus of elasticity, temperature, etc., and lastly we will look into part of the prediction, which would continue to the next lecture as well. So, let us see what is creep. Now, in material science, creep is the tendency of the solid or of any solid material to move slowly or deform permanently under the influence of stresses. So, basically it has a many materials have tendency to move slowly or deform permanently under influence of stress. Now, metal exhibits this under certain conditions, polymers also exhibit this, and of course, concrete does. Therefore, what it means is that it occurs due to long term exposure to stress, and obviously, they will be below the strength, because it will not fail. So, below that there will be deformation long term if you expose them to long term stress. That means, stress you have and you keep it, maintain the stress, it would show deformation, move slowly or deform permanently. So, therefore, that is what is creep. Creep occurs in metals, polymers and concrete. Creep of concrete is different than of course, others, creep of concrete is different than others. Mechanisms are different, because the materials themselves are quite different. So, let us see, supposing I have a concrete and I apply stress at some time t 0 as shown here. This axis is stress, this axis is age, and put it to some value of sigma 0, the stress level, and maintain the stress constant. Therefore, sustained loading, kind of sustained stress, right. So, expose it continuously, continuous exposure to a stress. Let us see what happens. Sustained stress as we have applied, then at the same time t 0, the strain would be elastic strain, because instantaneously there will be elastic strain due to this. So, there will be some elastic strain, because I have applied the stress. So, initial elastic strain will be given by this sigma 0 divided by modulus of elasticity of the material. And as the time progresses, you find there is some sort of deformation occurring, and if you consider the time t, when I have sustained the loading, as we have seen, we have sustained the loading t and beyond. So, at point t you find some additional deformation under this constant or additional strain under the constant sigma 0 is been observed. Sigma 0 you have not changed, but with time you find there are additional deformation, additional strain, and therefore, the creep at this point will be defined as strain at E t, which is the sum total of this. At t, it is sum total of E 0 plus the creep. So, therefore, E is E t minus E 0, that is what is creep strain after time t minus t 0. So, that is what is creep. Concrete exhibits this behavior, many other material does, but concrete does, that is what is of our interest at the moment. So, that is what it is. So, this resulted in strain, sustained stress, resulted strain. We find that there are two componented instantaneous elastic strain, and with time there will be some more strain, which is of course asymptotic to some line, and the difference between these two we call as creep strain or creep simply. If you look at the stress strain diagram, right, epsilon t, stress is sigma 0, same stress is sigma 0. So, instantaneous at E 0 is this much. So, this is my initial elastic strain, stress strain. So, this is the stress, this is the strain. As I increase my stress, it reaches to this strain, and let me keep it there, do not increase it further as is shown here, but the what will happen after 7 days of loading, you will find there is some increase, and further increase at any time you will find the strain is increased further at E t. So, therefore, creep is E t minus E 0. So, this is E t minus E 0, that is the creep. So, say some days and 7 days under load, 28 days under load, 100 days under load. So, at any time after t minus t 0 under load, stress strain behavior will change. In other words, effective modulus has also changed. Effective modulus has also changed. So, if I am considering at some later time, I find that the actually for example, if this is my stress level, instantaneous will be this much, and instantaneous will be this much, and this will be the creep. This will be the creep. So, instantaneous is this much, this will be the creep. If I consider this stress level, this is the instantaneous, this is the creep level, this is the creep strain. So, at any point of time, any level of stress, this occurs below the failures, below the strength level, and you find there is always creep. So, that is what is creep we have defined. We define creep like this, right. Now, a related aspect is relaxation. To understand relaxation, let us consider this pre-stressed concrete element, an element of concrete, just hypothetical element of concrete, something like this, just an element of concrete, and I have put a pre-stressing bar there. So, I have put a pre-stressing bar, it is stressed, tensioned, pre-tensioned, and then I have just so pre-stressing bar, this is what I have done. So, I have just pre-tensioned it, and this will result in a compression in the concrete. This will result in a compression in the concrete. Through this bar there will be resultant compression in the concrete. So, concrete will get compressed, and therefore, some elastic deformation would occur. So, it is reached to this level. This is the after the elastic deformation, it would have it would have actually shortened. Now, if I allow this continuously for a long period of time, actually I will find some deformation which I have not shown here, finally, over a long period of time I might end up getting further release of further compression of this whole thing, if I have just kept this material in the long run. So, this will be my creep, this will be simply creep, this will be simply creep, this will be simply creep, but then that is what we have explained earlier. Now, let us look at relaxation then. Okay. So, the creep was something like this. Now, what I do now, take this same after elastic deformation, take this specimen and then provide some restraint to this, provide some restraint to this. Do not allow it to shrink, as I was saying, due to creep it would have gone to this level, but I decided that I will restrain it and will not allow it to go to this level. So, what will happen? Net effect would be, because it is after creep its dimension should have been somewhere here, but I have restrained it. I have restrained it. This restraint means I am effectively applying a tension. I have, this restraint means I am applying a kind of tension, and this tension neutralizes the compression. So, the original compression which I have provided through pre-stressing is actually get reduced, it will get relaxed, and this is called relaxation. This is called relaxation, this is called relaxation, this is called relaxation, this is called relaxation. So, therefore, if I diagrammatically try to look at it, this is my edge, and then at T 0 I have provided sigma 0 like this before, and elastic strain is like this, but now instead of allowing it to deform further or the strain to increase, what I have done? I have restrained it. So, as I restrain it, the stress will get neutralized by the kind of a tension that comes in, because I have restrained it. Its natural position would have been somewhat different. So, it this, as we said, there will be a kind of, since it is restrained, there will be a kind of tension which will actually neutralize this sigma 0 value, and therefore, there is a reduction in the stress, and this is what we call as relaxation. So, relaxation, since the creep varies with time, relaxation will also vary with time, and since creep was it was something of this kind, creep was something of this kind, relaxation will be in the opposite direction. So, here is the stress, not the strain, here is the stress, stress get reduced, and relaxation at any age will be given at sigma 0 minus sigma t. So, this is your sigma t, this is your sigma t, this is your sigma t. So, this is the sigma t. So, sigma 0 minus sigma t. So, you see this, if it is restrained specimen, creep gets actually reduced, and through this pre-stressed concrete element that I tried to show you, actually what I am implying is that this is very important in pre-stressed concrete. We will just discuss about that sometime later on, where creep is important, very important, certain type of structures, or where in the situations where creep is important. So, this is what is relaxation. So, so far we have defined creep, and we have also defined what is called relaxation, what is called relaxation. Now, if I withdraw, what happens if I withdraw the stress? If I withdraw this stress, this was my strain original, and I withdraw the stress, right. So, time since application of the load. So, this is your T, and I withdraw this stress. Now, what I find is the strain, it actually comes down, it comes down, it comes down. So, this is, but then it does not come back to the 0 level. I have applied stress, this is the elastic strain, this is the elastic strain at sigma 0, elastic strain, then this is the creep strain, and then I just withdrawn the load completely. So, it comes back. So, this is actually instantaneous recovery, kind of some of the elastic strain will be recovered, but then it does not come back to the original state, it stops here only. So, this is creep recovery. With time, some amount of recovery occurs, this is called creep recovery. So, my residual deformation is here, residual deformation is here. So, there is creep recovery, there is residual deformation still remaining, and which it does not come back to 0. So, there is a residual deformation, and recovery will have two component. One is instantaneous recovery as soon as I remove the load, somewhat like elastic strain. So, instantaneous recovery of the strain, but after that gradual decrease, gradual recovery of the strain will occur, and that we call as creep recovery. Now, you can see that this is in two state. If it is stored dry and it is stored wet, if it is stored dry and if it is stored wet. In wet condition, of course, creep is somewhat less, it is stored wet completely, it is less actually, and then creep recovery is, but the behavior as far as further after unloading. the behavior is almost similar to whether you stored it dry or stored it wet. All right. So, this is creep recoveries, right. So, we have what we have seen? We have seen so far what is creep, relaxation, related phenomena, and how the creep recovery occurs. All right. So, we can proceed further, and by proceeding further we can look into mechanism of creep. So, we can proceed further and then we can look into mechanism of creep. Now, what is mechanism of creep? Well, actually the problem is except mechanism of creep is still unclear. It is not well understood as yet. There are of course, some kind of theoretical modeling being attempted, but there is a lot of debate on it. There are debates available on it. Okay. So, at the moment exact mechanism of creep of concrete is not clear, or creep in cement paste is not clear, but it is one thing understood that it is related to the gel and gel water. It is related to gel and gel system, capillary, the pore system of the concrete. So, gel pores related to gel pores. Generally, it is related to adsorbed or interlayer water. Generally, it is related to adsorbed or interlayer water. All right. And one thing has been observed that concrete after removal of all evaporable water exhibits little creep, exhibits little creep, exhibits little creep, exhibits little creep. Basically, if you remove all water, but then it might confuse you a little bit, because I said creep in wet situation. If it is fully saturated, completely wet situation, if you keep it, there will be no movement of water actually. But if you have removed all the evaporable water and then then try to study the creep, it shows that the creep is relatively less. So, therefore, it has something to do with those evaporable water or the water its presence. As I said earlier, that it occurs at all stress levels within the service stress range, that means before failure, and it has been observed that it is linearly dependent on the stress when the pore water content is constant. So, if you are not allowing it to dry or anything of that kind, seeing the pore water content is constant, then it is linearly related to the stress level, when pore water content is constant. So, it occurs at all stress level. So, there is something to the pore water level, that is what we are understanding. If you remove water, then you do not get creep really, it does not exhibit creep. So, therefore, it is related to adsorbed or interlayer or water present in the cement hydrate system, that can be understood. When drying occurs, I mean from saturated, see one case is you have dried it and then studying the creep, completely dry. But if you are looking at during the drying process, drying creep occurs when water moves out. Of course, shrinkage also occurs simultaneously. It is very difficult to separate out shrinkage from creep, because many cases both are related to water movement and the gel water gets involved in both the cases. So, it is difficult to actually separate them out, especially when you are studying the drying creep. And internal movement of water to empty pores in silt specimen causes creep. So, in silt specimen, movement of water to empty pores causes creep. See, you can understand there are some sort of the statement I am making, it is not, it does not straight away get into the mechanism straightforward. There are more complexities involved and the understanding is not yet clear. Certain observations are, one can list a huge number of observations that has been seen in laboratory, but generally it is attributed to movement of water and the adsorbed water and so on and so forth. Basically, it is a calcium silicate hydrate CHS of hardened Portland cement, and that's that's where it originates. That's where that's where it originates. In case of dried or when you have removed the water, that's what has been said, that creep is caused by slip due to bond rupture along the bond, along with bond restoration at the adjacent site when water is removed. So, when you remove the water, CHS has got van der Waals kind of bond, and this rupture of these bonds rupture of these bonds causing actually some sort of further deformation, and then of course, the bonds restores elsewhere, bonds gets restored elsewhere. So, movement of water from one place to the other actually causes from gel to some other place, from some gel to some other place, causes rupture of some of the bond which are associated with the water, actually the van der Waals kind of bond that we talked of in case of CHS gel. You know, it is across those interlayer water, that is what we mentioned in the beginning. When you remove the water, there comes some kind of slippages can occur due to bond rupture, but then water moves into somewhere else and there the bond actually restores. So, these are some kind of ideas that has been put forward, but one has to remember the cement paste or concrete, you know, I am talking of cement based concrete, hydration process is continuous, it does not occur instantaneously and it goes on occurring. So, this is what is actually you can say aging, you know, the material changes with time, and in any case you have large specific surface of the gel, and these ones have some roles to play in creep, these ones have some roles to play in creep. So, continuous hydration process, the change that occurs, the aging of concrete, and of course, large specific surface associated with the gel, the water getting absorbed there, and this have all some role to play in creep. So, concrete undergoes actually gradual changes in response to stress and environment, because hydration is also occurring, and if you have put in some stress, there is an interaction with the stress and the changes that is occurring, and it will also depend upon the environment, relative humidity and so on and so forth. Thus, it is actually extremely complex thermomechanical behavior, and you know, this exhibits extremely complex thermomechanical behavior, and creep is no exception. So, that is why it is so difficult to actually predict, but one thing we have understood from our discussion so far, that is related to the gel water and its movement, gel water and its movement, right, may be related to porosity and so on and so forth. So, as we see, we will see the factors affecting, we will have some idea, but exact mechanisms are still not very clear. So, now we can look into factors influencing creep. Let us see what are the factors that influence the creep. First of all, modulus of elasticity of aggregate, we will see more of it, but we can understand, you know, because the deformation of the concrete, if you are looking at it would be affected by modulus of elasticity of the overall material, and in the overall material aggregate modulus of elasticity plays a role. Therefore, modulus of elasticity of aggregate is an important one. Water cement ratio essentially governs the porosity and pore structure of cement based material, and therefore, water cement ratio will also, you know, is a factor that influences the creep. Curing condition, the environmental condition, whether it is fully saturated or what it is, the water movement is, you know, finally it is water movement, therefore, curing condition, and also it is a complex interaction of hydration process which continues over a long period of time. So, therefore, curing condition becomes important. Relative humidity, environmental condition we just mentioned before, and volume to surface area ratio is important, because depending upon volume to surface area ratio, evaporation rate, you know, the movement of water outside the specimen or outside the element would be governed by volume to surface area ratio. The slump is the flow of the concrete characteristics, and fine to total aggregate and air content, all these are the factors. So, these are the factors we will see how do they affect, and how one can, then we will look into how one can use this for predicting creep, All right. So, these are the factors. Let us see individually some one of them, how do they affect. Aggregate modulus of elasticity, this is an important part, and you find that as the modulus of elasticity of aggregate increases, the creep reduces, the creep actually, you know, relative creep reduces. So, higher modulus of elasticity, these are all in GPa, let us say something like 100 GPa or 60 GPa, you know, 60 GPa or 100 GPa. So, 60 GPa, 40 GPa, and relative modulus. So, very little is high, spaced sort of, very little. So, as the modulus of elasticity increases, creep will decrease. So, this is somewhere is a red sandstone, this is a green sandstone somewhere there, marble, river gravel, granite and crushed quartz, basalt and so on and so forth. So, as you increase, as the modulus of elasticity increases, creep reduces. So, higher modulus restrains creep. We can understand this very easily. Actually, creep means more deformation, but deformation, but if it is a higher modulus, stiffness of the aggregate is more, it is not going to deform. So, it will not allow creep to occur, it will restrain the creep somewhat, because the deformation would be restrained by higher modulus aggregate. Higher aggregate content of course, will also result in lesser creep. It is related, because aggregate does not creep, it is the cement paste which shows exhibit, which is responsible for creep of concrete. Therefore, more the aggregate content, lesser will be the creep. This we can see in this diagram. More the aggregate content, lesser will be the creep. You see volumetric content of the aggregate percent. So, this is 100% here, 0% here. So, it increases along this direction and creep in micro strain sort of. So, this some of them are for dry specimen, the rounded one, and these are for wet specimen, and this is creep from the edge